Hello everyone, I'm Jethro and I'm here to talk to you today about my FYP, Generalization Advantage for Quantum Recurrent Agents with Minimal States. So, I'm very sure that most of us would have heard of quantum computing in one way or another. Perhaps we may not understand everything about it, and even if we do understand some of it, we perhaps would have only known of some of the famous algorithms. For example, Shor's factoring algorithm, which solves factoring exponentially faster than a classical computer can. However, whether or not it is truly an exponential advantage has not been proven yet. This is because in theoretical computer science, complexity theory, we do not know firstly if P is equal to NP. Furthermore, there is no proof that factoring itself is an NP hard problem, and in fact, it is not believed to be an NP hard. So it is possible that perhaps there exists some sort of factoring algorithm which runs on a classical computer in polynomial time, which therefore proves that Shor's factoring algorithm does not give us an exponential advantage. There's also Grover search algorithm. In contrast to Shor's factoring algorithm, Grover search, which runs in O of square root of n times, has been proven to be a polynomial advantage, and it is in fact the optimal quantum algorithm that can ever exist. This is because we know that for any searching algorithm, without any assumptions in an unstructured database, this would require O of n time. Another famous algorithm is the HHL algorithm, which is utilized in order to find matrix inverses. This has been proven to have an exponential advantage. However, this is only true with some major caveats, as has been described by Scott Aaronson. Therefore, what am I trying to say? What I'm trying to say is that the problem in quantum computing as of now is that we do not know where we can get advantages. For example, we know that in complexity theory, it has been proven in 2009 by Rahul Jain that IP is equals to QIP. So from this image taken from the CQT website, it shows that when we have an interactive proof system with a polynomial time-bounded classical verifier, this is actually equivalent in terms of power to a polynomial time-bounded quantum verifier. And the both of these are actually equal to the class of problems which can be solved by having a polynomial amount of space, which means that we have the equivalence IP equals to P space equals to QIP. This shows us that just because we have a quantum system does not mean that we definitely can get an advantage over a classical computer. Therefore, what this project aims to do is to finally see through the lens of intelligent agents whether there exists some sort of advantage for quantum when we are dealing with intelligent agents with a quantum memory over those with only a classical memory. Now let me discuss what is an agent. An agent is a system which is an environment which is capable of taking in input stimuli, taking an action based on that stimuli, and receiving a reward based on the previous stimuli and the action that is undertaken and the new environment state that it is in now. So as we can see, the problem that we have is how do we build these agents? Well, the framework that is used commonly in order to build these agents is reinforcement learning. This framework allows us to learn directly from interactions with the environments. And actually, it has been developed in order to solve Markov decision processes. So let me introduce what a Markov decision process is briefly. Markov decision process is defined by having a state space S, a non-empty finite state space S, a finite set A of possible actions that the agent can take, a family of transition probability matrices, which describes the probability of us moving to a new state S of T prime, given that we take action AT from the previous state of S of T. And finally, we have a reward function, R, which is a function of the previous state and the previous action and the new current state that it's in. Based on this definition, we can see why this is called a Markov decision process. This is because the reward function only cares about S of t, A of t, and S of t plus 1. This means that regardless of the past history, we only look at the previous time step and the current state at the current time step. Now, when we look at a screenshot of a Pong game, as you can see here in the screen, a black and white screenshot, this is actually a Markov decision process. However, what are the states? Well, we can say that the states that are relevant to the agent who is controlling the paddle here on the right would be what is the velocity of the ball, what is the current coordinates of the ball, in what direction is the ball moving. And by seeing the shadow here on the ball, as you can see, we can tell that this ball is moving upwards and to the right. However, these are not states that we directly get from the environment, but we need to infer. So this Atari game, or this collection of Atari games, and in this example, Pong, actually forms a partially observable Markov decision process, a POMDP in short. This means that we do not have access to the state space S, but instead we have access to the observation, which consists of some alphabet O, which tells us what the current state is. And in order to extract the states, our agent utilizes 3 convolutional layers. After that, we pass the extracted features into an LSTM, which then outputs the Q value. And a Q value is a function of a state and an action, which tells us the utility of taking that action given that we are at this current state. So actually, it is just a CNN combined with an LSTM network. But because we are interested in agents, in classical agent, and then with finite memory states, this means that an RNN, which by its design has an infinite memory state because it takes place in a finite dimensional, a very high dimensional, finite dimensional Hilbert space, well, we need to discretize them into FSMs. And how do we discretize vectors in a finite vector space? Well, this can be done by clustering, ternary neurons, and L-star query. And we will be only talking about the first two because L-star query is used mostly for finite state acceptors and not finite state machines. Why do we use clustering? Well, because by the paper Michelenko et al., we see that the hidden state actually has a strong relationship to a FSM. And this can be seen in the pictures which they have shown, which shows the hidden states with its corresponding finite state machine. A QBN is a method to transform policies into a finite state representation, and they are autoencoders where the latent representation is discretized. And in the picture here is how it is done. What I have done in my project is to show that regardless of which discretization method that we are using, in the end, we obtain the same FSM with the same number of discrete states. This shows that these two methods, these two algorithms, produce the same finite state machine in the end. However, when we are analyzing one-way communication games, these methods actually do not produce the theoretical optimal finite state machine, and hence we have to look at more complicated games like Atari. This has been done through the game of Pong as well as other games, and in the future, what can be done is to train variational quantum algorithms in order to construct a circuit which learns these kind of environments. Thank you very much.